So far in this lecture series, our discussion has primarily been focused on precipitation radar. In this module, we'll explore higher frequency radar operating in the Ka and W bands, which are used for detection of smaller hydrometeors. Going back to the transmittance of an atmosphere containing an average amount of water vapor, the attenuation of our radar beam will generally increase with increasing frequency. In a previous module, we saw that attenuation at S-band was negligible for most applications, but that attenuation at even X-band was quite noticeable, especially in heavy precipitation and at long ranges. Ka-band, and certainly W-band, radar is much more susceptible to attenuation than the X-band, so its use is limited to short ranges and constrained by radar properties such as the intensity of transmitted power and the antenna gain. The high-frequency radars are called cloud radars because their shorter wavelengths are more susceptible to scattering by small, non-precipitating cloud drops that only have minimal impact on longer wavelengths. So we can see these hydrometeors that are in non-precipitating clouds. We would not be able to see them with the precipitation radar for the most part, unless they operated at very high power. Many cloud radars are vertically pointing, meaning that the antenna is fixed, only looks upward, and observes clouds as they pass over the radar. This picture shows two different cloud radars next to each other. On the left is a W-band radar antenna, and on the right is a Ka-band. Because of its longer wavelength, the antenna for the Ka-band radar is much larger. Vertically pointing Ka-band radar data may look something like that shown here. At the top is the radar reflectivity factor, and at bottom is the mean Doppler velocity. As before, negative radial velocities indicate motion toward the radar, which in this case is downward. The time axis progresses from left to right over the course of a day. Focusing on the reflectivity first, we see the leading edge of a precipitation system reach the radar, and high reflectivity in excess of 35 dBz is seen early on near the ground. In subsequent hours, the reflectivity is lower in the stratiform part of the precipitation system. And finally, by 18 UTC, rain mainly stops, but the radar can observe this non-precipitating anvil cloud with reflectivity less than 0 dBz. Typical weather radars would not see the non-precipitating cloud with such detailed structure, if at all. The 0 degree sea level is also very obvious in this type of vertically pointing data. Above this level, the power returned to the radar is generally lower due to the lower dielectric constant of ice, and the radar processor interprets this as a reduction in reflectivity. The background reflectivity of minus 30 dBz or less is noise and can be removed in post-processing by considering the signal-to-noise ratio. At the bottom, the radial velocity is generally downward toward the radar where precipitation is occurring, especially below the 0 degree sea level. The red colors are likely folded velocities such that they actually are strongly downward but are depicted as upward because they exceed the Nyquist velocity, which is actually much lower than that for most weather radar. The data can also provide other fields such as spectral width, shown at top, and the signal-to-noise ratio illustrated at bottom, which, as said before, is a useful tool for helping to quality control the radar fields and eliminate background noise. Precipitation radars that transmit extremely high power also have increased sensitivity and can detect features within precipitating and non-precipitating clouds that typical weather radars cannot. One example from the Pulse Doppler Mid-Course Radar, or MCR, near Cape Canaveral, Florida, is shown here. The radar is operated by the U.S. Navy and was previously used for tracking debris from space shuttle launches. By transmitting large amounts of power, the sensitivity of the radar is increased, such as seen by the minus 20 dBz echoes observed in the raining cloud pictured at top left, and that's those light blue colors. In fact, this radar can even see individual raindrops, shown here tracked in height and time on the x-axis, which is useful for remotely sensing the drop size distribution in clouds, a critical step toward improvement of microphysical parameterization. Most radars, however, do not have this capability. Scanning cloud radars are similar to the vertically pointing radars that we saw earlier, but they're mounted on a pedestal with gears that allows the antenna to rotate just like a precipitation radar. These are sometimes mounted in dual frequency configuration, such as the two examples shown here, which pair Ka and W band antennas on the left and X and Ka band antennas on the right. Compared to precipitation radar, the properties of scanning cloud radar are quite different. For example, scanning W and Ka band radars often operate with PRFs, shown here, of nearly 5,000 Hz, compared to roughly 1,000 Hz for S or C band radar. This greatly reduces the maximum unambiguous range of these radars, but this is acceptable considering that W and Ka band radiation get attenuated and would not complete two-way propagation over 100 to 150 kilometers anyway. Even though the PRF is much larger than precipitation radar, the Nyquist velocity is still smaller due to its wavelength dependence. In other words, the PRF increases by a factor of 5, but the wavelength of Ka or W band is a factor of 10 or more less compared to W band. The beam width and the gate spacing for cloud radar tend to be small, allowing for high-resolution observations over the shorter distance observed. And finally, the sensitivity for cloud radars, while dependent upon the properties of the transmitted radiation as well, is typically somewhere between -20 and -30 dBz. Newer radars are more commonly equipped with polarization agile transmission as well. While precipitation radars are largely used in operations and research, both cloud radars today are still generally used almost exclusively for research applications. Therefore, the scan strategies can be adapted to the particular research objective, and PPIs, like those used by weather radar, are not often used with cloud radars. Some different examples of scan strategies that can be used by cloud radars are shown here. The top left is a standard PPI, with the hollow cones representing different tilts, and the horizontal cross-section shown here, just examples representing flow that might be derived from a single Doppler retrieval of the data. The top right is a standard RHI scan strategy, and the bottom left is just your vertically pointing strategy, and then the bottom right is just an example of how a reflector with a known shape and size can be used for calibrating the radar. Other types of scan strategies usually are some type of RHI that may be used depending upon the application. The top left is called a hemispheric RHI, in which the antenna samples an entire 180-degree sector, like this, including overhead, before moving to the next pair of azimuths over to here and then back there. The top right is a standard RHI scan strategy, but modified such that the elevation angles only cover the boundary layer. The bottom scan strategies are sector RHIs that point vertically and at angles slightly off of zenith. These scans can be configured in a crosswind or a long wind orientation. An example of the vertically pointing sector RHI data is shown here as a crosswind scan for a convective cloud passing over a Ka band radar. Again, note the sensitivity of between -25 and -30 dBz. Unlike vertically pointing fixed antennas, a scanning radar can collect a three-dimensional volume of non-precipitating clouds, analogous to how a precipitation radar views a three-dimensional volume of raining targets. Such non-precipitating clouds might include shallow cumuli or stratocumuli, stratus clouds, mid-level cumuliform and stratiform clouds, or cirriform clouds. High-frequency radars used for cloud detection are also operated from space. A precipitation radar, which operated in Ku band, was aboard the Tropical Rainfall Measurement Mission satellite, which operated from 1997 to 2015. Although technically not a cloud radar, its operation at Ku band was much more susceptible to attenuation than typical weather radar wavelengths. TRMM was able to provide spatial maps of rainfall through the tropics and has since been replaced by the Global Precipitation Measurement, or GPM satellite, which carries a dual frequency Ku and Ka band radar system. An example of the swaths of the radar data, Ku and Ka are shown by the pink and the purple, or actually the Ku is green, Ka is purple. And the microwave imager swath for the same platform, this is the GMI swath, is shown over here. The Ka band radar is capable of detecting non-precipitating clouds more readily than the Ku band radar. The differential attenuation experienced between the two bands is also leveraged to identify rain and snow. To obtain a resolution in the troposphere of 5 kilometers by 5 kilometers at nadir, however, both antennas must be much larger than corresponding ground-based radars operating at the same frequency. The size of the radar system on GPM is seen at top left, next to a person for scale, while the bottom right image shows the companion ground-based radar operating at the same frequencies. GPM is part of a family of satellites that carry microwave imagers, such as those that we discussed in the previous lecture series. However, GPM is unique in that it carries downward-pointing precipitation radar. It operates in low Earth orbit, but it is in a prograde non-sun synchronous orbit, so that it can sample locations at various times of day, allowing for characterization of the diurnal variability in rainfall. It also operates at a higher inclination than the TRMM satellite did, which enables GPM to estimate precipitation over a wider band of latitudes. Examples of Ku and Ka band radar data along a swath following the GPM ground track is shown here. The swath of data, converted from reflectivity to rain rate in this particular example, is seen here at left. The cross sections at right follow the ground track along the black line in the left panel from A to B. At right is the radar reflectivity factor, although without numbers attached to the color scale. We're looking at altitude on the y-axis and then that cross-section length on the x-axis. Warmer colors denote higher reflectivity. Generally, the Ku band reflectivity is higher than the Ka band reflectivity because the Ka band beam is more heavily attenuated as it propagates downward through the atmosphere. An example of a global rain rate map is shown here. It is updated every 30 minutes and is derived partially from the GPM radar data, but largely from a combination of passive microwave and infrared brightness temperatures as well. Another downward-pointing radar is called Cloudsat. It is a W-band radar that is more sensitive than the radars aboard GPM and is more capable of identifying optically thin cirrus clouds and shallow cumuli. In the example shown here, Cloudsat, which is now part of the C-Train constellation with Calypso, passed over this tropical disturbance off the southeastern coast of the United States. The satellite was on its descending node and encountered 3 regions of clouds, moving from here down to here. A cross-section of the nadir-pointing cloud radar data is seen at bottom, with time shown along the x-axis, and the positions also noted in latitude-longitude coordinates. Non-precipitating cloud is seen at both high and low latitudes, altitudes. Note that in the deeper convection, the reflectivity is largest near the tops of convection, so it's very large here compared to down here low in the convection, and the same thing over here in this other cloud area. This happens because the W-band beam is attenuated rapidly as it moves down through the cloud. As a result, a minimal amount of transmitted power remains for backscattering from the lower troposphere. Thus, even though drop size distributions are probably large close to the surface, the space-based cloud radar cannot detect this. In contrast, in the same echo, a ground-based cloud radar would see the high reflectivity close to the surface, but would be attenuated rapidly with height such that it would not clearly see the top of the cloud. As a result, space-borne cloud radar is most effective for detecting the tops of deep convection and optically thick cirrus cloud, such as this right here, or the tops of the deep cloud right here. Vertically pointing cloud radars can also detect non-precipitating clouds at multiple levels. Ground-based or space-borne LiDARs, the LiDARs being a subject of a later module, operate at visible or near IR wavelengths and are especially useful for detecting optically thin cloud that radars are not sensitive enough to detect. Precipitating cloud is best observed from space, using lower frequency precipitation radars such as those operating in Ku band, or using ground-based or aircraft-based precipitation radar operating in XC or S bands. And the shallow non-precipitating convection in the boundary layer is best observed using ground-based or aircraft-based cloud radars to minimize the impact of attenuation on reducing signal strength compared to space-based radar. However, in the absence of heavy precipitation and with a minimal amount of water vapor if considering W-band, space-based radar or LiDAR might also detect such clouds. Any of these instruments may detect any of these types of clouds, depending on the properties of transmitted radiation and the range of the target. These are the most common applications, however, for the various instruments discussed in this lecture series.